Smell and temperature weave through everyday life. In hot drinks, forest air, warm spices, and familiar clothes that bring comfort and memory. But in interactive systems, smell is hard to control. Once released, odors linger, mix, and resist rapid change. Instead of manipulating scent itself, we ask, can odor perception be modulated? Here we present a wearable, nose-mounted thermohaptic interface enabling precise, closed-loop heating and cooling for modulating olfactory perception. The wearable adopts an eyeglass-style form factor designed to distribute weight across the nasal sidewalls, ears, and cheekbones. Its housing incorporates a constrained dual-arm mechanism that maintains consistent Peltier-skin contact while minimizing positional drift during head movement. To accommodate different facial geometries, the frame provides multiple adjustable degrees of freedom, allowing precise positioning of the thermal modules relative to the nasal sidewalls. ESP32 Development Board coordinates the system, managing communication and real-time control. A motor driver supplies the power needed to drive the thermal actuators. Two Peltier elements are mounted on a glasses-based frame to apply localized heating and cooling at the nose. Temperature feedback is captured through thermocouples and amplifier modules, enabling stable closed-loop thermal regulation. Overall, the system achieves rapid temperature transitions while maintaining stable and accurate steady-state control. We first conducted a psychophysical study to quantify how nasal thermal stimulation bias perceived odor intensity. Using a two-interval forced choice task and adaptive staircases, we estimated just noticeable temperature differences for heating and cooling across three odors: cherry blossom, sweet orange, and wasabi oil. Results showed that across all three odors, cooling yielded lower JND thresholds than heating, indicating higher perceptual sensitivity to cooling. Then, we examined how nasal thermal modulation reshapes odor quality perception. Using a multidimensional descriptor space, participants rated odor qualities under baseline, moderate, and threshold thermal conditions, allowing us to observe how temperature shifts the semantic structure of odor experience. Out of the 10 odor dimensions, only 2 showed consistent changes. When cooling was applied, the pleasant odors, cherry blossom and sweet orange, became noticeably fresher and sharper. We also found that stronger cooling led to more noticeable changes, suggesting the effect depends on temperature magnitude. For wasabi, the effect was different. Instead of increasing freshness, cooling reduced unpleasant and irritating qualities. In contrast, heating produced only minor changes across all odors. Overall, this suggests that temperature selectively reshapes specific aspects of smell, rather than affecting all qualities equally. Here, we outline 4 possible use cases. Attenuating pungency for food. Some foods, such as wasabi, can be strong-smelling. By applying a cooling sensation near the nose, it may be possible to reduce how intense these odors are perceived. Selective qualitative tuning for odors. Users may subtly adjust different qualities of an existing ambient smell, such as increasing minty notes by applying a cooling sensation. This could allow individuals to shape their sensory experience based on personal preference. VR, contextual adaptation and scent reuse. A chocolate aroma, for instance, could be perceived as ice cream when paired with cooling, or as hot cocoa when paired with warmth. Ambient well-being and attention shaping. Temperature shifts occur gradually over time, potentially influencing how scents are perceived. These gentle, wave-like changes could act as ambient cues, supporting relaxation, meditation, and focus. For detailed methods and analyses, please refer to the paper